On this worksheet, we're going to be looking at nucleophilic addition reactions that involve nucleophiles where the oxygen atom is attacking the carbonyl carbon. The first reaction that we're looking at is called the formation of a hydrate. This reaction only works with formaldehyde. It's a super unfavorable reaction, and formaldehyde is the only molecule that is reactive enough for this reaction to work. The hydrate molecule is shown right here. It's a 1 carbon molecule that has 2 OH groups attached, so you can see how it's formed from the formaldehyde molecule. I'm going to highlight the formaldehyde molecule over here, and then I'm going to highlight the portions of the hydrate molecule that have come from the formaldehyde. So that right there, and then the hydrogen and the OH are added from the H2O in the nucleophilic addition process. The OH group is adding itself to the carbonyl carbon, and the hydrogen is adding itself to the carbonyl oxygen. This reaction takes place under either basic conditions or acidic conditions. We're going to draw the mechanism for both of these possible reactions. I'm going to start by just drawing out the formaldehyde molecule. Under basic conditions, when we're dealing with basic conditions, that means that our nucleophile, our reactants, and all intermediates, so everything is either negatively charged or neutral. Those are what we see for all of our intermediates and reactants under basic conditions. So keeping this in mind, that everything needs to either be negatively charged or neutral under basic conditions, what would be a reasonable nucleophile for this reaction? The nucleophile begins the reaction by attacking the carbonyl carbon. So the component of our product that adds itself to the carbonyl carbon is the hydroxide. Our reasonable nucleophile for this reaction would then simply just be the hydroxide ion. It is exactly what we need in terms of atoms, and it's negatively charged, which is what we need for the basic conditions. So the nucleophile and the basic mechanism is going to attack the carbonyl carbon, which opens up the carbon-oxygen double bond, and the nucleophile is now bonded, forms a bond to the carbonyl carbon. Negative charge on the oxygen atom of the carbonyl group. The second step of this reaction, we just simply protonate the O- with something like water, and then the reaction is done. This gives us the product. I've drawn it in a way that looks a little different than what we have showing up here. The 2 OH groups up here are just side by side, but there is our basic mechanism. And again, this reaction also works under acidic conditions, so let's draw that particular mechanism. Under acidic conditions, everything in the reaction, the intermediates, the reactants, everything is either positively charged or neutral. So when we're drawing this mechanism, we want to make sure that we follow that rule. Under acidic conditions, the reaction begins by an acid protonating the carbonyl oxygen. And this problem is telling us to just use H3O plus as that acid. So this is what we're going to be starting with. Oxygen of the carbonyl group being protonated by that acid, which is going to look like this. And there's that positive charge that we need to be able to see. And the protonation leaves the H3O plus as just a water molecule, HOH. Lone pair of electrons on the oxygen of the water molecule are going to come in and attack the carbonyl carbon and open up the carbon-oxygen double bond. That's going to give us this guy right here. And then we are simply going to deprotonate we'll use another water molecule. Deprotonate using the oxygen of another water molecule. And this will give us the hydrate. And again, this reaction only works with formaldehyde, no other aldehydes, and no ketones at all. Reaction number 2 that we're going to look at, very similar. This is called the formation of an acetal. An acetal is this molecule right here. And again, it's very similar to a hydrate, but instead of OH groups, it has OR groups instead, so some alkyl groups as well. The reaction is done with any aldehyde or ketone, so this works for both aldehydes and ketones, reacting with two alcohols in the presence of an acid. This reaction does not work under basic conditions, so this is only an acid catalyzed reaction. For the acid that's typically used in this reaction, H2SO4 sulfuric acid or TSOH, those are the most common acids that we see used in this reaction. This reaction is very reversible. That's something that I'm going to talk about on the next page of the worksheet. So knowing that this is our product over here, I'm going to do the same thing that I did with the formation of the hydrate. I'm going to highlight the ketone that we're starting with, and then highlight the components of that ketone that show up over here in the acetal. So in this reaction, we are adding an OR group to our carbonyl carbon, and then we are adding an R group to the oxygen up here. Let's take a look at how this reaction works. Under acidic conditions, we're going to use HA to represent the acid catalyst right here, and then we're just going to use generic ROH for the reaction. So I'm going to start with the ketone. We're going to start with our acid HA. Even though this reaction is in equilibrium, same with the hydrate reaction in equilibrium, I'm just going to simplify things by only writing the forward arrow. Anytime you have an oxygen in the presence of an acid, you should begin by protonating the oxygen atom, and that's going to give us this intermediate right here, like that. And then in the next step of this reaction, one of our alcohol molecules, and I'm just going to abbreviate that ROH, one of our alcohol molecules is going to use a lone pair of electrons to attack the carbonyl carbon and open up the carbon-oxygen double bond. And that's going to give us this molecule right here. So this mechanism looks very similar to the formation of the hydrate. And then we are going to deprotonate this molecule right here. The deprotonation can be done with another alcohol, or it could be done with the conjugate base A-. I'm just going to use the conjugate base A-. It could also be done with water. There's a lot of different things that we could use for this particular step in the mechanism. And the molecule itself is just going to, use whatever it has available. So this we've made right here, we're, halfway to an acetal. We've got one of those OR groups added. This molecule is actually called a hemiacetal. Hemi, like for half. It's halfway done. And we could stop the reaction at this point if we wanted. The formation of the hemiacetal is very, it's very favorable, it's very stable. If we only put in one alcohol, this is what we're going to produce, just the hemiacetal. But if we have lots of alcohol present, the reaction is going to keep going. In the second step of this reaction with the hemiacetal, we're going to use that acid again, same acid, HA, and we're going to use this acid to protonate an oxygen. We've got two oxygens available, and we could protonate either one of them. If we show the protonation of this oxygen right here, we're just reforming this molecule right here. Remember that this reaction is in equilibrium, so this process is actually happening. Some of this OR is being protonated, backing the reaction up. I'm not going to draw that because we're trying to draw the steps that show the reaction moving forward. So I'm not going to draw the protonation of the OR oxygen. I'm just going to show the protonation of the OH oxygen, and we're going to remember that everything is being protonated in this reaction. So I've got my OH protonated right there, like that. And what's going to happen next, so things are kind of going to deviate a little bit from what we saw in the formation of the hydrate. What we've made here is a really nice leaving group, looks really good. So we're actually going to do that. We're going to put this oxygen lone pair of electrons back into the carbon-oxygen bond, and we're just going to get rid of that water molecule entirely, like that. Now this is going to be a really ugly drawing. I've got some pretty gross bond angles going on here, but we're not going to worry about that right now. This is the molecule that we've made. So again, we've just gotten rid of this water completely, and we've made kind of a ketone-ish looking sort of a thing. And then, okay, I can't really stand this weird, no, I'm going to leave it. I was going to change that drawing, but I'm just going to leave it. Then what we're going to do is bring in alcohol number 2. Alcohol number 2, lone pair of electrons on the oxygen, are going to attack that carbonyl carbon and open up the carbon-oxygen double bond once again. And so now we have this molecule right here, like that. We've added our second alcohol molecule, and all that we have to do to get to the hemiacetal is just deprotonate one more time. Again, what we use for the deprotonation, we've got a lot of stuff available to us. We could use the A-. I'm just showing it being done with A- again, but we could use another alcohol for the deprotonation. We could use water for the deprotonation. And here we now have the acetal. And again, it looks a little different from the drawing because I have my OR groups on the other side of the molecule, opposite sides of the molecule, but it is the acetal molecule. Now let's talk a little bit about what we can do with these acetals. They're actually very useful molecules. And one of the application of the acetal, the formation of the acetal, is to use it as what we refer to as a protecting group. Because acetals are really easy to put on molecules and take off of molecules, they work really well as a protecting group. As a reminder, a protecting group is when we take a functional group and we temporarily transform it into something that is non-reactive, and then do some sort of reaction with the rest of the molecule. And then when we're done, we just convert the functional group back to what it was originally. So here's an example of how we could use the acetal to do protection on a ketone, starting with just acetone. If we use a diol, so instead of having two alcohols, we have one molecule that has two OH groups. Still works the exact same way as two separate alcohols. We can form an acetal using this diol. It looks, it's kind of looks like a person. The diol is used to form the acetal. These oxygens are connected to each other, so it makes this cool little acetal right here. This is what we would refer to as a protected ketone. So we've got this ketone that has been temporarily converted into a non-reactive acetal. We could do some sort of chemical reaction, and then when we were done, we could just reverse the formation of the acetal and bring back the original ketone. To reverse the formation of the acetal, all that we have to do is add some water in the presence of acid, and it's just going to put itself right back. This is really helpful for situations like, let's say, a Grignard reaction. Here is a molecule that has two carbonyl groups, a ketone and an ester. And let's say that we wanted to do a Grignard reaction on the ester, but not on the ketone. Ketones are very reactive with Grignard, so it would be impossible to do this reaction just with putting a straight Grignard in there. The Grignard would react with both of the carbonyl groups. But what we could do is temporarily convert that ketone to an acetal, because the formation of the acetal only works with aldehydes and ketones. It does not work with esters or carboxylic acids. So we could make this molecule right here where our ketone has been protected by the formation of the acetal, but the ester is still available. And then we can do our Grignard reaction. It looks like in this Grignard reaction, we're using a methyl Grignard, CH3, MgBr. We would need excess of that. And then follow that up with H3O+. The H3O+ is necessary for the second step of the Grignard reaction, and the H3O+ is also simultaneously going to deprotect our ketone. So all at once, this H3O+ is going to finish the Grignard reaction and convert the acetal back into a ketone. So that's pretty handy. Now, one of the things that you want to be able to do is take an acetal and deprotect it or convert it back to a ketone or an aldehyde. In the lab, it's a really simple process. All you have to do is just put a little acid in your solution, but on paper, it can be a little bit tricky. So here are some examples of that. And what's going on here is we have an acetal and we're subjecting it to some acid, and we're trying to figure out what the ketone is that will be formed once this acetal is converted back to its ketone. Now, you could solve this type of problem by going back to the mechanism for the formation of the acetal and just working your way backwards through the mechanism. That's actually pretty tedious and pretty easy to make a mistake because it's hard to follow those mechanisms in reverse. So a shortcut to help you solve this type of problem, I want you to find the two oxygen atoms of the acetal, and I also want you to find the carbon atom that connects them. That's where all of the chemistry is going to take place in this reaction. reaction. The carbon atom that is in between those two oxygens, I'm going to call it the acetal carbon. That's a name that makes sense. This carbon atom was at one point the carbonyl carbon. And in the deprotection process, it's going to be turned back into the carbonyl carbon. So over here, I'm going to draw this molecule again, OET, OET, and we're just going to basically kind of dissect it. Here's our acetal group right there. And as I said, this is my carbonyl carbon. So what I'm going to do is I'm going to pick either one of these oxygens to be my carbonyl oxygen. And I promise you, it does not matter which oxygen you pick. So this is going to be my carbonyl carbon, and I'm going to choose one of these oxygens to be my carbonyl oxygen. I'm just going to choose the one that's on the left. That's usually what I choose. So I want my carbonyl group to end up right here in this spot right there. And to do that, I'm actually just going to make this double bond right there. I'm going to go ahead and draw a C in there for that carbon. In order for me to put a double bond in between the carbon and the oxygen, I've got to get rid of some bonds in this molecule. Right now, what I have drawn for this poor carbon is 1, 2, 3, 4, 5 bonds. That's way too many. The bond that I'm going to be getting rid of is that bond between the carbon and the other oxygen. Like boom, that bond needs to be broken in this process. Separate it. Also, I've got too much stuff on this oxygen as well. This oxygen has 2 bonds to the carbon plus 1 bond to the ethyl group. That's way too much for that oxygen as well. So I'm going to separate that from that as well. We're always going to be, busting this up into 3 pieces. What we have left with right here, that is a beautiful ketone. That is one of the products of this reaction. The other 2 fragments that we've made here, these are coming from the 2 alcohols that are used to form the acetal. And what we need to do is just add a hydrogen to one and an OH to the other to give us the formulas of the 2 alcohols that are produced in this deprotection reaction. So there are 3 products, 2 ethanols, and then this cyclohexanone. Let's practice again with this next one down here. And again, I'm going to start by kind of sketching out the acetal again, like that. I want to begin by finding my acetal group, the 2 oxygen atoms, and the carbon that connects them. I want to pick one of the 2 oxygen atoms. It doesn't matter which one. I'm going to pick one of these 2 oxygen atoms to be my carbonyl oxygen. I will choose the oxygen on the left, and this is my carbonyl carbon, and this is my carbon-oxygen double bond. Once I have made that carbonyl group, I've got too many bonds to that carbonyl group. So remember, I need to break this bond right here, break the bond to the other oxygen, the one that I didn't choose, and break off whatever is attached to my oxygen as well. So I need to break this bond, and I need to break this bond, and I need to pull this piece away. Now here we've got just, one chunk. We need to this molecule here, we need to add an H, and we need to add an OH like that. And there's our 2 products. Let's practice again with this next example right here. I'm going to redraw it. Like I said, this is a pretty tricky reaction, but once you've practiced it, and as long as you follow these same steps, you're going to get the hang of it. So we want to find our 2 oxygens and the carbon that connects them. The carbon that connects them is the acetal carbon. We're going to pick either oxygen. I always pick the one on the left, so this time I'm going to pick the one on the right. Pick this oxygen to be our carbonyl group. Once we've made our carbonyl group, we need to break the bond from the oxygen that we didn't pick. And we need to break the bond on the oxygen atom, the other end as well. And then we need to complete the molecule by adding an OH and an H. This is just one molecule. It's got the ketone and the 2 alcohols all in one. One more example for us to look at. This one, for the first time, this is the first example where we're looking at an asymmetric acetal. So around the acetal group, the molecule is not symmetrical. We're not going to change our strategy though. We're going to, we want to find our 2 oxygen atoms and the 1 carbon atom that connects them, and we can pick either oxygen atom. And even though it's asymmetrical, seriously still, you can pick either one. It's not going to make a difference, I promise you. So you can pick either one of these oxygen atoms. This time I'm going to pick the one that's on the right-hand side. So I'm going to pick the oxygen on the right-hand side. That's going to be my carbonyl group. Once I've made the carbonyl group, I need to isolate it. I'm going to isolate it by breaking the bond between the carbonyl carbon and the oxygen that I did not choose. So I'm going to break that bond right there. And I'm also going to break the bond to the other end of the oxygen. Now I need to add an H and I need to add an OH. And if you're not, like if you just feels like there's no way that I would get the same product if I had picked the other oxygen atom, let's just do it the other way as well. We'll do it just so that you can see, have evidence that it genuinely does not matter which oxygen you pick. So we'll go this way. Here's our carbonyl carbon, and this time I'll say we're gonna make this the carbonyl group right there. So I made the carbonyl group. I want to break the bond to the oxygen that I did not choose, and also now this is going to be kind of weird. I need to write in the CH3. I'm going to break the bond off the other end of the oxygen right there. Pull this apart. Now I just need to add an OH and an H. And look, they are the exact same product. So it genuinely doesn't matter which one you choose.